Hi guys, welcome back to Crack Easy, the place to learn how to crack easy exams. You are with me Abhisha. Today I'm here with a session on elementary discrete time signals. Why we are studying about this, or what is the significance of this topic in signals and system? Any guess? Okay, let me explain. In fact, the characteristics of systems are being studied by applying elementary signals into its input and analyze corresponding output. So, if we want to do detailed analysis of systems, we should apply different types of elementary signal into its input. Or in other words, we can say that we should know about different types of elementary signals. That's why we are doing this session. As I told you, today we are going to look at different elementary discrete time signals. I hope you're already aware of what is discrete time signals. What is that? It's nothing but a signal where the independent variable time can take only discrete set of values. Let me ask you something. Do you know how to represent a discrete time signal? Alright. First, we will have a look at different representation methods of discrete time signal. Then we will be concentrating on our topic, elementary discrete time signals. In fact, there are 4 representation methods for discrete time signals. They are graphical representation, functional representation, tabular representation, and sequence representation. Actually, a discrete time signal can be given in any of these 4 representations in your upcoming GATE or any other competitive exam. So you should be familiar with all of these 4 representation methods. Let us understand this one by one. First, we are going to focus on graphical representation. I'm going to explain all of these 4 representations with an example. So consider a discrete time signal x of n, which is having non-zero values only at 3 time instants. That is, x of n at n equal to minus 1 is 1, x of 0 is 2, and x of 1 is 3. This is a graphical representation of x of n. The independent variable n is plotted along x-axis and the signal amplitude along y-axis. At n equal to minus 1, value of x of n is 1. So we draw a straight line representing amplitude 1 at n equal to minus 1. And at n equal to 0, value of x of n is 0, 2. So we draw a straight line at n equal to 0 representing magnitude 2. And so on. Got it? Let me now take you to next representation, functional representation, where the discrete time signal is represented as a function. Here, x of n is written as 1 for n equal to minus 1, 2 for n equal to 0, and 3 for n equal to 1. Next, we have tabular representation, where the discrete time signal x of n is written in a table. You can see the independent variable n is written along first row of the table, and corresponding signal amplitude is written along second row. From the table, it is clear that at n equal to minus 1, x of n is 1, at n equal to 0, x of n is 2, and at n equal to 1, x of n is 3. Finally, we have sequence representation, where the discrete time signal is represented as a sequence of numbers within a pair of set brackets. The origin of the discrete time signal is indicated by an arrow symbol. You can see an arrow symbol under number 2 here, which means the value of x of n at n equal to 0 is 2, at n equal to 1 is 3, and at n equal to minus 1 is 1. Let me ask you something. If the arrow symbol is not given, how can we identify the origin of discrete time signal? In fact, if the arrow symbol is not given, the first element should be considered as value of discrete time signal at n equal to 0. Got it? Hope you understood all of these 4 representations perfectly. It's the time to start our topic, elementary discrete time signal. First, we are going to look at unit step sequence. It is represented as u of n and mathematically defined as 1 for n greater than or equal to 0 and 0 for n less than 0. This is the graphical representation of u of n. The independent variable n is plotted along x-axis and the signal amplitude along y-axis. You can see it is having a constant amplitude 1 at n equal to 0, 1, 2, 3, etc. Next we have unit ramp sequence, which is defined as r of n is equal to n for n greater than or equal to 0 and 0 for n less than 0. This is the graphical representation of unit ramp sequence. At n equal to 0, its value is 0. At n equal to 1, its amplitude is 1. At n equal to 2, it is 2, and so on. After that, unit impulse sequence, which is one of the most important elementary discrete time signal from analysis point of view. It is represented as del of n and mathematically defined as 1 for n equal to 0 and 0 for n not equal to 0. This is the graphical representation. You can see it is having non-zero value only at n equal to 0, and at n equal to 0 its value is 1. Then we have exponential sequences, which is represented as x of n is equal to a raised to n, where a is a constant. Now we are going to plot x of n for different values of a. If a greater than 1, it's a growing exponential which look like this. You can see as the value of n increases, its amplitude grows exponentially. On the other hand, if a is in the range 0 and 1, it will be a decaying exponential which looks like this. As the value of n increases, its amplitude decreases or decays exponentially. If a less than minus 1, it will be like this, and if a is in the range minus 1 to 0, we get a waveform like this. Clear? Finally, we have sinusoidal signals, discrete time sinusoidal signals, which can be mathematically written as x of n is equal to a cos omega 0 n plus phi, where omega 0 is the frequency in radian per sample and phi is the phase. This is the graphical representation of x of n. So now we are at the end of this session. Hope you all enjoyed it. Thanks for watching. Thank you.